All right, gotta hurry. We're going to talk about mass defect and binding energy. All right, it's kind of interesting. Everything you've ever been taught about conservation of mass and conservation of energy is completely untrue. People have been lying to you your whole lives, kiddies. They just have. All right, there is something called a mass defect, and that defect becomes binding energy, and I'll explain that to you in just a bit. But what I want you to realize is this: what you're used to calling conservation of mass is an example of things that are fairly large. Like I'm going to move this camera over to right there, and that's a fantastic example. That's a drum kit. You guys all know if I put that drum kit on a scale, the scale will give me a number. Who cares what it is? I don't know. It doesn't matter. But what you then also know is, what if I disassemble that drum kit? And what if I put each individual piece on a scale and then add up all of those individual pieces? If I push the plus button, they will all add up to the sum of the parts will equal the mass of the whole thing. And that's very, very true. That's conservation of mass from that aspect. But what if I were to do that same procedure with something and the sum of the masses doesn't equal the mass whole? And that's what I'm going to talk about now. When you do that with atoms, individual atoms, take an atom, put it on a scale, it'll give you a number. Then if you take that atom apart and put the individual protons on a scale one at a time, individual neutrons on a scale one at a time, individual electrons on a scale one at a time, push the plus button, it will not equal the same number. All right, that difference is called a mass defect, and what that mass defect becomes is binding energy. All right, an example I will use for the math: lithium-7. Okay, the mass of the whole thing for lithium-7 is 7.016004 U's. What U's may remember is that comes from this chart right here. Look to the left, not quite to the bottom all the way. You see lithium with the 7 right there. Its atomic mass is 7.016004. 92.41% of all lithium is that. All right, so that's where that number comes from. It is not the atomic mass of lithium, which is 6.94. That is something covered in a different topic, but please know, lithium-7, its mass is not 7. We get very, very specific, 7.016004. All right, kiddies? Now, that lithium-7 then has a mass whole of that. If its A number is 7, that's its mass. Its Z number is 3. That means it's got 3 protons, 3 electrons, 4 neutrons. What I'm going to do is add up those parts. There are 3 P pluses, each of those protons, 1.007267 U's. Now, this number right here will be given to U's should U's need it. It's something you can look up anytime. That's the mass of a proton in U's. There are 4 neutrons, and that number, very, very similar to the mass of a proton. Neutrons are just a hair heavier in U's. That number will always be given to U's, and this is the mass of electrons. There are 3 of them, and they're very, 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 very small compared to the other stuff. The reason I'm including electrons, even though this is nuclear physics, is because the mass on this data table that is communicated in terms of the mass of the atom does include electrons in it. All right, so it's the mass of the whole and entire atom. So all I did is I'm going to multiply these together, get a number, multiply those, get a number. I'm going to push the plus button. I'm going to add up the sum. I'm going to add up the sum of the individual smaller pieces. And when I multiply 3 times 1, I get 3.021828 U's. And when I multiply 4 by this, I'm getting 4.03466. It gives you 1 fewer digit. If you want to fill it in with a 0, go right ahead. If you don't, it don't matter. This guy, 3 times 1, this is going to be a very small number, 0. There's going to be 2 zeros, a 1, 6, and a 4, and a 7. All right? So all I'm going to do is push the plus button. I'm going to add all of that together. That's the sum of the individual masses. All right? Add all that together. I promise you will get 7.058 135 U's. That's the mass of the whole thing. All right. Now, what I need you to realize is, though, take a look at that number, 7.058135. What it isn't is the mass that was communicated on that chart, the mass that is a whole and entire atom. This mass is larger than the mass of the whole atom. So when those pieces come together to form an atom, they lose mass. Well, where does that mass go? Or actually, let me calculate the difference first. So what I'm going to do now is push the minus button. All I'm going to do is subtract this number here, 7.016004. So I'm going to subtract 7.016004, push the minus button, and that difference right there, 0.042131 U's, is the difference in mass. So the mass defect is the change in mass. Now, what does it do? Where does it go? What happens to it when protons come together? They have an electromagnetic repulsion force. They don't want to hang out together. It takes a certain amount of energy to hold the nucleus together. I mean, you guys know that. It takes a lot of energy to hold your stuff together, doesn't it? So that's what binding energy is, the energy that expresses itself in order to hold that item together. So if you lose mass, you're going to gain energy. So mass isn't conserved, energy isn't conserved, but if you put them together and say those two items are two different expressions of the same thing, then together they are conserved. I jokingly call it massergy. Massergy is always conserved, okay? It becomes binding energy. What we'll learn a little later on is there is a force inside a nucleus that must be stronger than the electromagnetic repulsion of protons, because Paula Abdul taught us opposites attract, like charges repel. They want to fly apart. So there is a force that starts to express itself inside a nucleus. It's called a strong force because it's got to be strong like magnetic repulsion. We'll learn more about that in an upcoming video. But for right now, binding energy. It's what holds a nucleus together. The mass that is lost in the assemblage of the parts is becoming expressed as energy. So you guys all know this equation, E equals mc squared. Energy is mass. Mass is energy. Equal means ish the same, right? So those two items are the same. The ratio of energy to mass is the square of the speed of light. E equals mc squared. So if I want to know the mass of something, I could take its energy and divide it by the speed of light squared. 1 U's worth of mass, it turns out, 2's have, this is the number U's will be given if you ever need it. It is 931.5 million electron volts per C squared is 1 U. All right, that's a conversion. They usually don't write the per C squared, okay? They usually don't write that because it's always going to be, if you want to solve for a mass over here, this equation, mass is always going to be energy divided by that same C squared. And since C is constant, the square of C is constant. So it's just easier to not even write the per C squared. So what we could do to get the number of electron volts holding one lithium-7 nucleus together, I'm going to take this difference in mass, multiply it by that conversion, and what we'll end up with is 0.042131 times 931 is 39.2 million electron volts for every atom of lithium, provided it's lithium-7. Now what I'm going to do is give you a slightly different way to word it. Instead of electron volts, I'm going to go with joules because joules are usually a little more easily visualized. What I'm going to do is take that mass and multiply it by the speed of light squared to get energy in joules. The only thing is that mass needs to be in kgs. If I'm going to do this, whoops, I almost wrote kjs. If I'm going to do this in joules, I'm going to turn it into kgs. All right, so what I'm going to do to turn that into kgs is I'm going to take that number, 0.042131 U's, and I'm going to say that's 1.66 E negative 27 kilograms for every 1 U. So that dies, and I'm going to get a number in kilograms now. How many kilograms is that difference in mass? And it's not a lot. It is 6.99 and 37, however many digits you care to keep there, times 10 to the negative 29th kilograms. That's a difference in mass, okay? That's the mass defect. What I'm going to do is multiply that by the speed of light squared. C is 3e8 squared. That becomes 9e16. So if I take this number right here, 6.9930 negative 29 kilograms, that's the mass defect. If I multiply it by c squared, I'm going to get the binding energy. There is 6.29 times 10 to the negative 12 joules in every one atom of, in this case, lithium with a mass of 7. Now, that's not a lot because it's joules per one lonely little atom. But do you remember your chemistry teacher taught you something about moles? And if you want to know how many atoms are in a mole, you just multiply it by the number I call 6 kajillion. Avogadro's number, 6 kajillion, is 6.02 times 10 to the 23rd. If this is how many joules is in one atom, multiply it by 6 kajillion. The atoms die, you're in joules per mole. Look at that number, 3.79 times 10 to the 12th joules per mole. That's a big number, 3.7, 3.8. The 10 to the 12th is a terajoules, 3.8-ish trillion joules per mole. That's a lot. And another thing just to remember, usually that would be a happy number. That's an answer. That's a good number to say. What's the binding energy per mole? They would say that 3.8-ish terajoules per mole. Oftentimes, though, since Einstein used equals mc squared, what's the energy per mass? Well, do you know, in lithium 7's case, you remember your chemistry teacher taught you that the atomic mass is the number of grams per mole. So what if I say I'm going to take that and divide it by 7 for the case of lithium 7 now? It's that many joules per mole, which means it's that many joules per 7 grams. So if I just divide that by 7, I'm going to get 5.414 joules per gram. All right, times 10 to the 11th. 5.414 times 10 to the 11th joules per gram. 10 to the 11th, now that's joules per gram, okay? Just 1 gram, like a paperclip-ish worth of mass. Now, if that 10 to the 11th is a little bit awkward, I'm going to move it over to call it 10 to the 12th, 0.5-ish, about a half-ish 10 to the 12th, about a half-ish terajoule per gram. Okay, now grams are small, so what would that be per kilogram? It'd be 1,000 times more, about a half-ish times 10 to the 15th joules per kilogram. 10 to the 12th, I said over here, is a terajoule. 10 to the 15th is a petajoule, all right? Just to give you an idea, this is about a half a trillion. I'm sorry, that's a half a trillion. This is about a half of 100,000, 500,000 terajoules. All right, 500,000 terajoules per kilogram of this stuff. 500,000 terajoules is what this, 0.54 e to the 15 joules per kilogram. Now, I have this written here because just to give you an idea, joules, how much energy is inside 1 kilograms worth of lithium, all right? I looked up the bastion of all things true, Wikipedia. The little boy bomb dropped on Hiroshima. 63 TJ, 63 terajoules. That was the little one. Fat Man, 84 terajoules. So 63 and 84 terajoules. 63 TJ, 84 TJ. All right? Remember, 10 to the 12th is a tera. This is 10 to the 15th. I have about a half at 10 to the 15th. There is more energy in 1 kilogram of lithium nucleices, a lot more, 500,000 terajoules compared to 63 and 84 terajoules that were dropped on those unfortunate folks there that day. But just to give you an idea, boy, there's a lot of energy in mass, okay? It takes a lot of energy to hold things together. And when you break those nuclei, boy, you release a lot of energy. And that's what I was just trying to show you with that comparison, okay? What I'm going to have you guys do is calculate mass defect and binding energy for 2 different nuclei, helium-4 and iodine-127. I went ahead and wrote out what those atomic masses are for those individual pieces. Just do it in kilojoule or just joules per mole, and if you need to convert into a terajoules, kilojoules, whatever, but do it in joules per mole, and there's 15 minutes. Yay Physics